Okay, so for this part of the unit, we are going to talk about how carbon dioxide is being transported. And first of all, let's just start off with carbon dioxide. When it's being produced by respiring tissues, it's going to end up being sent back to the lungs via the bloodstream. So carbon dioxide will end up in the blood to get back to the lungs. And how it gets back to the lungs is slightly different. So 5%, it can just dissolve in the water, in the plasma. It's not much. 10%, the carbon dioxide can bind with hemoglobin to form something called carbaminohemoglobin. So that's another way it can get back to the lungs. And the most common way, 85%, it's going to return in the form of hydrogen carbonate ions, which is written down here, HCO3-, or here as well, we can see HCO3-. So we're going to spend most emphasis is going to be about these hydrogen carbonate ions. We're also going to link this part of the unit back to the oxygen or the hemoglobin dissociation curves, because CO2 affects it, and we call this effect the Bohr effect. And it's all to do with the fact that when CO2 builds up in the bloodstream, it causes the blood, that environment, to become acidic. And it's all to do with this molecule here, carbonic acid, this compound, carbonic acid, H2CO3. So already I've just mentioned H2CO3, and I've mentioned HCO3-. I've just also mentioned carbaminohemoglobin, so already quite a few words. All right, so I'll introduce you to a few more as we go through this. So let's focus on hydrogen carbonate ions. So as CO2 builds up in the respiring tissues, that is going to cause an increase in concentration, and therefore it's going to diffuse down the concentration gradient into the bloodstream. And the CO2 is going to react with the water, CO2 plus H2O, in the presence of the enzyme carbonic anhydrase, is going to produce carbonic acid. And like all acids, one thing they've all got in common is they all donate hydrogen ions. So there's our carbonic acid up here, H2CO3, breaks down into the hydrogen ion, which is what makes it acidic. And then you can also see it's broken down into the hydrogen carbonate, HCO3-. Let's just follow the HCO3- first. So if this HCO3- is building up in the red blood cell or the erythrocytes, a concentration gradient is going to be created, and it's going to diffuse out of the blood cell. And when that happens, it takes the negative charge with it. So if negative charge is diffusing out, it's causing the inside to become positive, and that can be balanced out by a process called the chloride shift. So chloride ions are being pumped in to counteract any negative that was leaving. These chloride ions are going to be pumped in to maintain that same charge, so it's a neutral charge. All right, let's follow what this carbonic acid does. So we know it's broken down into hydrogen carbonates, and it's also been broken down into the hydrogen ion, which is what's causing the acidity. Some of these hydrogen ions, they can actually bind with hemoglobin. So not only does hemoglobin bind with oxygen to form oxyhemoglobin, it can bind with carbon dioxide to form carbaminohemoglobin, and also hemoglobin can bind with hydrogen ions to form hemoglobinic acids and HHB, and this is acting as a buffer. So it's helping to prevent the environment getting even more acidic, because acidity can cause problems. Any enzymes that are present, such as carbonic anhydrase, if the environment gets too acidic, this could perhaps become denatured, and that could cause problems as well. And there's lots of other enzymes as well. All right, so we've discussed carbonic anhydrase, chloride shift, hemoglobinic acid, carbaminohemoglobin, hydrogen carbonate ion, which is HCO3-, and carbonic acid, H2CO3. So the first difficult part I would say is CO2 is reacting with water to form this compound here, H2CO3, carbonic acid, which is then breaking down into hydrogen carbonate and the hydrogen ion. So just to remember that part. The hemoglobin is acting as a buffer because it is able to pick up some of these hydrogen ions, and that's helping to stop the environment getting too acidic. All right, so let's talk about we're going to go back to this oxygen dissociation curve. I want to ignore this line and this line. Just focus on the first line, and this should be familiar to you. We talked about this idea that hemoglobin, when there's low partial pressures of oxygen, it's not very good at associating with oxygen. Then as the partial pressure increases, it makes a very, very steep increase. It gets very, very good. As those heme groups get exposed, they start to pick up the remaining oxygens, and it becomes almost fully saturated. So that's the normal one. Now, this same oxygen dissociation curve it can change depending on how much CO2 is in that environment as well. So the original hemoglobin dissociation curve shows partial pressure of oxygen. If that increases, we see that the hemoglobin becomes more and more saturated with oxygen. Now we've got another variable to talk about. What happens to this dissociation curve if there are different partial pressures of CO2 present as well? So these three lines are showing different partial pressures, and as we move to the right, we're seeing that partial pressure of CO2 is going up. And what effect is that having? Right, well, I've marked this line here and this bottom line here. So the same hemoglobin molecule, if that same hemoglobin molecule is put into a partial pressure of oxygen at, roughly, let's say, just say 4 kilopascal. Originally, if that hemoglobin molecule was placed in a partial pressure of 4 of oxygen, the saturation was something like 20%, should we say. If that same hemoglobin molecule is in the same partial pressure of oxygen, but there's an increase in CO2 from 3 kilopascal to 6 kilopascal, so let's compare these two lines. You can see now this curve is looking much lower down. So at the same partial pressure, it's only something like 10%. So something's happening here. As you increase the partial pressure of CO2, the same hemoglobin molecule in the same partial pressure of oxygen is associating with less oxygen. Or you could word that another way. The same hemoglobin molecule in the same partial pressure of oxygen, but with different CO2 concentrations, is showing differences in how much oxygen is dissociating. So the hemoglobin molecule in an environment where there's a partial pressure of 6 kilopascal of CO2 is releasing 90% of its oxygen, or dissociating with 90%, hence why there's only 10% here. Whereas this one here, it's only dissociated with 80%. So this is really convenient because the parts of our body which are producing the most CO2 are also the parts of the body that needs the most oxygen, because this is where the respiration is occurring. So this Bohr effect is really useful, so that more oxygen ends up being released in tissues where more carbon dioxide is produced. Perfect for muscles. Right, so quite a bit of information there. Again, these different reactions, you need to remember these ones. You need to know how carbonic acid was produced and the enzyme that was involved. You need to be able to recall that this carbonic acid breaks down into hydrogen ion and hydrogen carbonate, and that hydrogen carbonate diffused out. And with that diffusing out, it took its negative charge out. So chloride ions had to be pumped in, and then we call that the chloride shift. We discussed that hemoglobin is acting as a buffer because it can bind with hydrogen ions to form hemoglobinic acids. And then finally, how this acidity can actually, that's the last thing to mention, yeah. So all I've mentioned to you so far is that this CO2 is causing, we can see here, the CO2 increase is causing more dissociation to occur. And this all comes down to the fact that hemoglobin is a protein. And if the protein is in an environment where there's more CO2, it's also an environment where it's more acidic. And that acidity is causing the hemoglobin's tertiary structure to slightly change. And that's going to cause it to have a lower affinity to oxygen. And if there's a lower affinity to oxygen, it's going to dissociate with that oxygen as well.